Hello dear student, I am Rejeena and I will be dealing with a portion in your chapter Molecular Spectra from your paper Atomic and Molecular Physics of Semester 5 Physics. In this chapter, we will be learning about Raman Spectra, classical and quantum theory of Raman scattering, vibrational Raman spectra, rotational Raman spectra, diatomic molecules and polyatomic molecules, the Raman spectrometer, the electronic spectra sequences and progressions, and also the Frank-Corin principle. The references of mine for this chapter is Dr. S.L. Gupta and Dr. V. Kumar's Element of Spectroscopy, The Modern Physics by G. Aruldas and P. Rajgopal, and also Modern Physics by R. Murugesan. In this video, we will be dealing with the Raman effect, the salient features of Raman spectra, the classical theory of Raman effect, and we will look into why the classical theory of Raman effect has failed. In the year 1928, Sir C.V. Raman observed an effect in his institute. A colored light entered a liquid and a fraction of the scattered light was of a different color. He found that this different color, the shift in this frequency, was independent of the incident radiation. And this effect is known as the Raman effect. This effect of shifting frequency was successfully explained using the classical and quantum mechanic effect. Still now, Raman effect is used as an analytical and research tool in physics and chemistry as a non-destructive analysis technique. For this discovery, he was awarded a Nobel Prize 2 years later in 1930. Now let us see what is a Raman effect. When an incident radiation interacts with a substance, two different scattered lights emerges from that substance, and this scattered light consists of the frequency of the incident radiation. It has a frequency which is higher than the frequency of the incident radiation, and it has a ray of light which has a frequency which is lower than the incident radiation. That is, whenever a light hits a substance, the scattered light consists of three different waves with the same frequency, with a higher frequency, and with a lower frequency. And this effect is known as the Raman effect. The Raman effect is a form of scattering in which the frequency of the incident beam undergoes a definite change, and this was observed by Raman in 1928. And this shift in frequency is known as the Raman shift. The Raman shift is the shift between the incident radiation, the frequency of the incident radiation, and the frequency of the scattered radiation. The frequency of the incident radiation and the scattered radiation can be zero, and this is known as the Rayleigh scattering or the Rayleigh lines. And this variation can be positive, that is the delta nu, the Raman shift. The difference between the incident frequency and the scattered frequency can be positive. That is, when the frequency of the incident light is higher than the frequency of the scattered light, then we will get stroke lines. And if the incident frequency turns out to be lesser than the scattered frequency, then the Raman shift is negative, and we will get anti-stroke lines in the Raman spectrum. The delta nu, that is the Raman shift, is a characteristic of a substance, and it does not depend on the incident light. So this technique can be used to determine what kind of the substance that is. The interacting substance will determine the Raman shift. and the Raman shift delta nu falls in the range of 100 centimeter to 2000 centimeter inverse. That is, it falls in the near IR regions. In the near IR regions, which means the energy shift is in the near IR regions, and that is this transition or this corresponds to the rotational or the vibrational energy levels. If it was in the electronic energy levels, then these regions have to be of visible or higher IR regions. Since it is near the lower IR regions, the energy is much less. So we can assume that this transitions or whatever this effect is from is due to the rotational or vibrational characteristic of the substance in which these are interacting. We can also see that the stroke lines, that is, when the Raman shift is positive, the stroke lines are more intense than the anti-stroke lines. Now let us see the Raman spectra. As we have already seen, when a light interacts with a matter, there are three types of scattered radiation coming out from that matter. And the first is the characteristic radiation, that is, the radiation which consists of the same frequency as that of the incident light. Then we have stroke lines. Stroke line consists of the radiation. Then we have stroke lines towards the lower frequency side of the characteristic line, and we have anti-stroke lines towards the higher frequency side of the characteristic line. And we can see that the stroke lines have a higher frequency compared to the anti-stroke line, but the characteristic line or the Rayleigh line here has a very high frequency, a very high intensity considered to the stroke lines and the anti-stroke lines. Comparing stroke lines and anti-stroke lines, the stroke lines have a higher intensity. When we zoom into or when we look into a higher resolution image of the stroke lines and anti-stroke lines, we can see that it is not just a single line. It consists of multiple lines in an ordered fashion. Therefore, and this splitting of lines is as a result of the rotational spectrum. When we further zoom into some of the lines, we can see that in addition to the pure rotational spectrum, we have it is altered with another type of lines here. They are the vibrational additions. They are alternated by vibrational additions. So the stroke lines here are not single. They composed of different radiation. It comes as a package. When we zoom into, we will see different radiations, and these lines are separated. These are equally separated lines, and this splitting of lines occur to rotational interaction with the electronic transition. And when we further zoom into, we can see that in addition to these lines that is occurring from the rotational spectrum, the vibrational interactions gives us another set of lines here, and they are also alternated and they are differed with an equal distance. For polyatomic molecules, we can see similar structures along the either side of the spectrum. We have to notice that the stroke lines falls into the lower frequency side and the anti-stroke lines falls into the higher frequency side. Here, since we are plotted with lambda or the wave number, we can see the reverse effect, that it falls into the stroke lines falls into the right side and the anti-stroke lines falls into the left side of the spectrum. So the salient features of the Raman spectra is it has the same line it has a line of the same frequency as the incident radiation, and this is known as the characteristic line or the Rayleigh line, and this line is very intense. Then we have lines on the lower frequency side which is known as the Stark lines, and we have lines in the higher frequency side known as the anti-Stark line of the spectrum. And the Stark lines are more intense than the anti-Stark lines. On higher resolution, we can see equidistant lines, and this arises from the pure rotational interaction. On further resolution, we can see the lines, that is the Stark lines and the anti-Stark lines, are alternated and composed of a fine structure with the vibrational rotational interaction. The rotation-vibration interaction of the polyatomic molecules give rise to several other set of these lines on the either side of the spectrum. Now let us try to explain this phenomenon using classical theory. We know that it is interacting with light. So matter is interacting with light, and light is an electromagnetic radiation. So if the electric field or the magnetic field have to interact with something, then it have to have something of an electric nature or a magnetic nature. It is easy for us to assume that these atoms or molecules have an electric nature since they have charged particles such as electrons and nucleus inside it. So let us use this classical theory to explain the effect we have seen so far. So when an atom, when it is interacted with an electric field, its electron cloud get disturbed and the electrons and the nucleus are separated. Similarly, in the case of a molecule, when it is interacted with an electric field, the electron cloud is disturbed and the oppositely charged particles are accumulated in opposite sides. So this can be considered as two equal and opposite charges separated by a distance. And what is that? It is a dipole. So we have two equal and opposite charges separated by a distance. And this is a dipole with a dipole moment P. So using this, we are explaining it. So a moment or a molecule, when it is placed in a field, electric field of strength E, a dipole moment is induced on it, and this induced dipole moment P is given by alpha into E, where alpha is a polarizability, or which is the tendency of a particle to get polarized. So the P is alpha times E. But we know that this particular E is not a constant radiation. It is a radiation. It is not a constant field. Since the radiation, it alternates, right? It alternates as a sine wave or a cosine wave. So considering it alternates as a cosine wave, we can write the electric field E as E0 amplitude into cos of 2 pi nu 0 t, where nu 0 is the frequency with which the electric field alternates. Therefore, the induced dipole moment P become alpha into E0 cos 2 pi nu 0 t. When a dipole is alternating, or when the dipole moment is alternating, we can say that it will emit radiation. When a dipole is rotating or oscillating, then it will emit radiation of the same frequency as its oscillation. Here we can see that this is the frequency with which this dipole oscillates. So it will emit radiation with the same frequency as nu 0. So when a dipole oscillates, it emits same frequency as the incident radiation. and this explains our Rayleigh scattering. So far we have explained the Rayleigh scattering, that is, this dipole is going to emit a radiation of the same frequency as the incident radiation. But we couldn't explain how the stroke lines or the anti-stroke lines, how we couldn't explain Raman shift. So to explain Raman shift, we will consider the internal motions such as vibration and rotation. So on considering the internal motion, we can see that the polarizability changes when we consider internal rotation. The polarizability alpha of a diatomic molecule when we consider vibration. For example, in case of a diatomic molecule, say if this molecule is vibrating with a displacement x from its mean position, then the change in the polarizability alpha can be written as alpha 0 plus beta into x, which is the displacement, by a, which is the amplitude of vibration. We know that from simple harmonic oscillator, x is equal to a cos 2 pi. Let nu v be the vibrational frequency, then it is 2 pi nu vt. On substituting this to here, we can see that the alpha, the polarizability, changes as alpha 0 plus beta, which is a constant, into cosine of 2 pi nu vt, where this nu v is the frequency with which the molecule vibrates. And when we incorporate this alpha into our previous equation of dipole moment, we can see that we can replace alpha with alpha 0 plus beta cosine of 2 pi nu vt into E0 cos 2 pi nu 0 t. Here nu 0 is the incident frequency of the incident radiation, and nu v is the frequency of vibration of the molecule. And here we will get three terms. First term is alpha 0 E0 2 pi cos nu 0 t. This is similar to what we have seen in the previous slide, and this will give rise to the Rayleigh scattering. Again, we have this term that consists of beta E0 cosine of something into cosine of something. How will we solve this? We know that 2 cos A cos B is equal to cos A plus B plus cos A minus B. So here we do not have 2, so we will just divide it with 1 by 2, and we will get beta E0 divided by 2 into cosine of 2 pi into nu 0 plus nu v and nu 0 minus nu v. Here the nu 0 plus nu v will gives us the stroke lines, and the nu 0 minus nu v part will give us the anti-stroke lines. So using the classical theory, we have successfully explained how the Rayleigh lines, the stroke lines and the anti-stroke lines occur in the Raman spectra. Similarly, considering the rotation, when it is rotating with a frequency nu r, when this molecule is rotating with a frequency nu r, we can see that it also gives the similar frequency, that is, here we get the Rayleigh scattering, and also this term will gives us the stroke lines, and this term will gives us the anti-stroke lines. So here the nu v is the vibrational Raman shift, and 2 nu r explains the rotational Raman shift. So we have explained how this hyperfine structure, we have earlier seen that we have hyperfine structures. So this explains the hyperfine structures we see in the Raman spectrum. But this classical theory of Raman effect has certain merits and demerits. The first merit, we can say that this explains how even homonuclear molecules, that is the molecules with which doesn't have a permanent dipole moment, also shows a Raman spectrum. We have molecules such as oxygen, nitrogen, etc. showing a Raman effect. So these homonuclear molecules are usually not much active when we take usual vibrational spectrum or rotational spectrum. In case of a usual vibrational or rotational spectrum, they are found inactive since they have no permanent dipole moment. But when we are taking Raman spectrum, we can find a characteristic line for homonuclear molecules such as oxygen, nitrogen, hydrogen, etc. So we know that in Raman effect we need not have the molecules to have a permanent dipole moment, because the permanent dipole moment here is induced by the electromagnetic radiation. So these homonuclear molecules can show Raman effect. And this theory explains why this homonuclear molecules, even though they doesn't have a permanent dipole moment, shows this Raman effect. The demerit of the classical theory of Raman effect is that when we have seen that in Raman spectrum the stroke lines are much more prominent and intense than the anti-stroke lines. But according to this theory, we have seen that occurrence of both these terms, the stroke term and the anti-stroke term, has the similar possibility. Therefore, the intensity of occurrence of the stroke lines and the anti-stroke lines must be same. That is, stroke line and anti-stroke line should have the similar intensity, which is not the case. So, the demerit of this classical theory is that it couldn't explain why the stroke lines are much more prominent than the anti-stroke lines. We will try to catch up this particular idea with the quantum theory. By this, I end this lecture. We will see in the next video. Thank you.